Let us start today's lecture on shear center. We have discussed yesterday what is the definition of shear center and how we can foundate its position itself. The surface of the being is supposed to be not subjected to any tangential force, and their boundary of the system is an unloaded boundary itself. The shear stresses and near the boundary don't have a complete perpendicular to the boundary. The shear stress near the boundary lines are parallel to the boundary itself. Hence, a thin section shear stress can be taken parallel to the central line of the beam. The location of the shear center depends only on the geometry itself. That is the shape of the section. This shear center can be on the beam itself, also can be away from the beam itself. This location of the shear center depends on the distribution of shear stresses tau x I and tau ix, yz, etc. But thin wall beams, approximate location of the shear centers can be determined by an elementary analysis, which we have discussed already. Already we have discussed, and I will go further toward that. Now, all the beams which carries loads are transverse in the axis of the beam, which may not only cause normal stresses, but due to create certain shear stress itself. But itself, the value of tau xy are determined by the equation of equilibrium countable on itself. The value of sigma x of flexural stress is given by the flexural formula. Now, one important point is here: the float P, external load, is acting over our concerned beam. In addition to causing moment, it also twists the beam itself. But P should be applied in such a distance from the centroid that twisting should not occur. That is the important thing, because we have to apply the load P, and P has to be the load P, in addition to the causing bending, will also twist. But P can be applied in such a distance from the centroid of the beam itself that twisting does not occur itself. So, for a section with symmetry, the load has to be along the axis of the symmetry to avoid any twisting. So that for the same reason, a beam with a general cross-section load P must have to be applied at a distance E from the CG, centroid. When the force P is applied to the z-axis, now the question is here, we have to do the load P, we have to apply at a distance E from the centroid, and the loads to be applied in the Z parallel to the Z-axis when the position should be established for which there is no rotation of the centroidal axis, centroidal elements of the cross-section. The point of intersection of these two lines is of great importance. This is called as the shear point, or the shear center itself. Now we have already discussed different portion of this, how to calculate, how to find out the shear portion. Let us go to some more details, some of the practical problems today. Now here, say, determine what is the given in the problem is, please determine the shear stress. Just a second. Determine the shear stress at a channel section. This is the section is now, here in this problem, what we have here, It is the problem is of the cross section of the channel is of this beam is channel in the shape of a channel, and it is embedded in the wall. So it is a cantilever beam itself, and the load it is subject to the load F, which is shown that it is not acting over the body of the channel itself, but it is acting over some projection of the channel. So it is away from the center of gravity of the channel itself. Now, if the cross section is magnified and put here, what we will see is that there is the principal stresses O, Y, Z, and principal stress OX, principal plane OX is acting normal to the plane of paper itself. And what we have here is the length of the channel from not from both the ends, but more or less center of the of both the flanges are equal to H itself. And the length of this channel along its curvature itself is given as S is equal to 0 at this point and equal to S at this point, as we have discussed on this point for a curvature of a beam. And the shear center or the centroid is acting at through O or the CG itself. And the distance from OY and OZ, OY and OZ is away from a distance Y for a sectional beam here. And the thickness of this beam is not equal everywhere. Here in this case, we are having the thickness equal to T1, and here in this case, having the thickness equal to T2. So thickness is not same, but other dimensions is length is equal to H and width is equal to B, which is more or less same here. Now, that OYZ is the principal axis itself. Means OZ is one of the principal axis and OY is another principal axis. And as per our theory and principal stresses, the second moment of inertia let OYZ be the principal axis, that is high YZ is equal to 0 from equation 6.3, then noting F is the negative here. What is given in this earlier equation in this surface is like this. The shear stress is given by the formula tau XS or SX is equal to minus By, the both vertical load